We're going to now transition into talking about moving charges, which really is the key to circuits and current, and that's going to be a big idea moving forward. And so let's start by just talking about a battery in general. So we have a battery here. We see here there's the negative side of the battery and the positive side. And the basic idea of a battery is you have a buildup of electrons here on the negative side of the battery, and those electrons want to go to the positive side. However, when you just have a battery sitting in your cabinet or on a shelf or something, they have no way to get from that negative side to the positive side. And these dashed lines here are actually showing what's called the electric field, which is something we didn't really talk about, but that just shows visually that desire or that impulse for those electrons to want to go from the negative side to the positive side. However, if we connect a wire, we can allow those electrons to go from the negative side to the positive side. And the process, we can make them do something for us by making an appliance work or something along those lines. All right, so this is what we were talking about on the last slide here. We said before that the battery has that positive side and that negative side. And basically there's that buildup of electrons on the negative side that all want to go to the positive side. And the fancy word we use to describe this desire of those electrons to go from the negative side of the battery to the positive side is potential difference. So we would say there's potential difference between the negative side of the battery and the positive side. However, as we said before, in order for that to happen, right, a battery on its own can't allow it to happen. What we need is a complete circuit. We need some sort of a pathway that lets the electrons travel from one side to the other. And what we typically are going to do is we're going to put some appliance or light bulb or something else within that pathway, forcing the electrons through that as they travel from the negative side to the positive side, and then turning on the light bulb or the appliance or whatever it is. So batteries are typically rated based off of what's called their potential difference. Now, this is the fancy formal word for it. The word you've probably heard used before to describe this is just the voltage, okay? Voltage is the more familiar, less formal way of saying this. But potential difference is technically the correct term for it. And it basically represents the energy that the electrons have as they move from one side of the battery to the other. So the more potential difference or more voltage that we have, the more the electrons want to go from one side to the other, and the more energy they'll release as they travel from one side of the battery to the other. Technically, it represents the energy per charge, so the number of joules per coulomb, but really, if we just think of it as the amount of energy the electrons have, that's a perfectly fine way of thinking about it. This term voltage comes from the units for potential difference. So the units for potential difference is the volt. And so it has been termed voltage. Potential difference is the proper term, but we'll just end up using volts. Many people do. But I do want you to know that potential difference is the correct term for this. So when we're in a lab and we want to measure the potential difference, we can either use a device called a voltmeter or a multimeter, which basically acts as a voltmeter but also can be set to be a number of other things related to circuits. Whenever we do measure potential difference, what we always do is we place the two sides of the voltmeter or the multimeter across whatever we want to measure the voltage across. So right here we have something called a resistor, which we haven't talked about yet, but we will get that. We will get there. And so if we want to measure the voltage or potential difference across the resistor, we would place each terminal of the multimeter on either side of the resistor, and that would measure the amount of energy that the electrons give off, all right, which is really the potential difference or the voltage across that resistor. The fancy term for how we're measuring it is we would say we're measuring it in parallel as opposed to in series, which we'll talk about in a little bit. But it is important, really, the key idea is that when you're measuring the voltage, you put those two probes, all right, on either side of the object that you want to measure the voltage across, connecting it in parallel. The next quantity we're going to talk about here is current. So current measures the amount of charge flowing through the circuit, which really just represents the number of electrons going through the circuit in a given time. We can measure the current in units of amperes, which is really just 1 coulomb per second. All right, that's the definition of an ampere. It's 1 coulomb of charge per second. So this really is a measure of the electron traffic going through the circuit in a given time. We're going to eventually get to an equation that's going to describe the relationship between current and voltage, but I do want you to know it's really important that they are two different quantities, and it is possible to have a high voltage and a low current. It's also possible to have a low voltage and a high current. So, for example, you could have a lot of electrons flowing through the circuit, but each individual electron doesn't have a lot of energy. That would be an example of high current, because it's lots of electrons, but low energy, so low voltage. Or the reverse is possible. You could only have a few electrons, which would be a low current, but a very, very high energy, which would be a high voltage. So it's important to keep in mind that while they're related, they are not the same quantity. When we go to measure current, current can be measured either with an ammeter, or once again, we can measure current with a multimeter, which, as we talked about before, it can act like a voltmeter. It can also act like a ammeter. Hence it being a multimeter, it has a lot of different functions. In both cases, when we're measuring current, we actually have to, the way I was thinking about it is we actually have to break the circuit. So we originally had our circuit connected like this, all right? And what we ended up doing was we disconnected the circuit, and we are basically forcing those electrons to go through our multimeter back the other side and complete the circuit. So whenever we're measuring current, this is how we have to do it. We have to break the circuit and force the electrons to go through our multimeter or our ammeter, all right, in order to measure that current. The way we talk about this connection is we say it's connected in series, not in parallel like we did for the voltmeter, but we connect it in series and force those electrons through the multimeter before it gets back around. We're not going to do a ton with this equation quite yet, but we will in a little bit in the next part of this unit. But I do want to put this out there. We do have a way of mathematically calculating the current, and that is this equation here. The current is delta Q over T, which really just means it's the amount of charge that passes through a given point, that's the delta Q, divided by the time it takes for that charge to pass. And so you can clearly see here that relationship between the units for current, amperes, and what it really represents, which is coulombs, the amount of charge, over the time, seconds. So coulombs per second gives us amperes. And this is how we would go about calculating the current if we knew how much charge was flowing in a given time. One quick thing, and again, we'll come back to this a little bit later. Keep in mind that the charge of an electron is 1.6 times 10 negative 19th. That is that fundamental charge that we've talked about before. And so there will be times when maybe we know the number of electrons flowing through a circuit, and we'll have to use our knowledge of how much charge an electron has in order to ultimately calculate the current. The last quantity we're going to talk about related to circuits is resistance. So almost every object, even objects that are conductors and are designed to allow electrons to flow, have some resistance or impedance to the movement of electrons. All right. So I don't necessarily want you to think of it as slowing down the electrons, because that's really not an accurate model in your head. But a better way of thinking about it is it basically causes the electrons to expend some amount of energy. Okay, so resistance measures how much a particular object resists the flow of current and forces those electrons going through the circuit to basically use up some of the energy that they have. All right. We measure resistance in units of ohms, which is symbolized by the Greek letter here, omega. That's what this is here. It kind of looks like a horseshoe, I think. And the amount of resistance we have depends on the type of material, so what it's made out of, and also the size and shape of it. We're not really going to get into figuring out how much resistance particular objects have. It's typically going to just be something that you're told. And there will be objects that we use in the lab that are just called resistors, and they're basically just made out of some material, and they have some set amount of resistance when current is flowing through them. Okay, so the important thing you need to know for now is just that resistance kind of measures how much opposition there is to the flow of electrons through a particular object.